Today we're going to be taking a look at related rates. Now let's think about what these two words mean. We have different rates going on and they're related to each other. Take a look at this picture. We have some water flowing into these gutters, which has a certain rate of flow going down into this tank. It looks like we have some water coming out as well. So the reality is the rate coming in might be different than the rate coming out. Also notice that the volume in this tank is going to be increasing. It has a certain rate in which it's increasing. All of these are related because, as you can see, the water all flows into a continuous path. So related rates just means rates in which things change, and those rates are related. We're going to look at several examples today to illustrate this concept. The way I'm going to be teaching this lesson is in steps. So each video will be individual steps. The reason we're doing that is because it can be very involved. Basically, you're taking pretty much everything you've learned in calculus and putting into one lesson. Rather than trying to do one example at a time, I'm going to do one step at a time to help solidify those concepts. Let's go ahead and read example 1 together. We have water pours into a fish tank at a rate of 0.3 meters cubed per minute. Now, I want you to underline a couple things here. First of all, every time you have a number in a word problem, you need to underline it. So we have at a rate of 0.3 cubic meters per minute. We need to underline that because it's a number and it's important. It's a rate. This is related rates. How fast is the water level rising? I'm going to underline that because that's what we're trying to answer. If the base of the tank is a rectangle of dimensions 2 by 3 meters, so again, we want to underline these two numbers because they're important and we need those numbers in order to solve this problem. And when you read a question, how do you know this is a related rates problem? Well, as we read through this question again, we can see that there are different rates going on. First of all, we have a rate of how much volume is being poured into the tank. Then we have another rate, which is how fast the water level is rising. Okay, now we can see that down here, the dimensions of the tank, that rate is constant. Okay, it's not like you can collapse the tank or adjust it. It's a box basically of a shape, a rectangular prism. So even though it's not a rate, we still need these numbers to solve this problem. The question is, what do we do for our first step, which is again what we're going to focus on in this first video. Well, the first step is to draw a labeled picture. I might even say the pre-step is to underline some key words here, but as you draw the picture, you might go back and find some more stuff that you didn't underline. So I drew a picture of a fish tank, which is a rectangular prism, and I labeled the dimensions, which are 3 by 2 or 2 by 3, whichever way you want to draw it, doesn't matter. I inserted a couple more things here. I said that the area of the bottom must be 6 square meters, right? Because 3 times 2 might not matter, but if you notice something, go ahead and fill it in. Now, we want to figure out how much the water level is rising as the water is dumping into the tank. So I labeled the height of the water H, okay? Now it is important to realize that's not the height of the tank. And in fact, it won't matter, right? It won't matter what the height of the tank is because the rate at which it's rising is going to be the same as long as this stays the same and it's rectangular. Now, if it were a cone, that'd be different, right? We'll talk about some of those problems later on. Okay, and then I drew, just the water coming in at a rate of 0.3 cubic meters per minute. What do I have down here? We want to be thorough when we draw this picture because if we miss something, then we might not ever see how to solve the problem. Okay, another thing that I labeled was the volume of the water. Okay, how can we figure out the volume of the water at a particular point in time? Well, remember the volume of a rectangular prism is length times width times height. So we could see it would just be 3 times 2 times whatever the height is. But again, like I said, you want to be thorough, so I basically labeled everything. So that's our picture for the first example. You're just going to draw a picture, and you're going to write everything down that you can and be thorough. Now, we draw a picture just because we are visual as humans and really helps us to understand the concept better when we draw a picture. This is a very important step, and it might be the most important when solving related rates problems, especially when they get more complex. So that's this. That's the picture for step one. Again, we can kind of see what we're trying to solve for. We want to figure out how fast the water level is rising. So let's say it's rising 1 meter per minute or something. That's what we're trying to figure out, okay? As the water pours in at 0.3 cubic meters per minute. So drawing a picture will help you understand basically what you're trying to solve. And another question you might want to ask is, do I have enough information, right? We said this one we do because the level in the water that's rising is going to be constant as this pours in. We should have enough information. We're just going to have some use some calculus to get there. That's step one for example one. Let's go ahead and look at example two. Again, I'm just going to look at drawing pictures in this video because I think it's just really overwhelming if you try to do all steps at once with a related rates problem. But if we do step by step, even when you do your assignment, you're going to get the feel for how to solve these. Example 2, a 5-meter ladder. Now remember, every time you have a figure, go ahead and underline that. A 5-meter ladder leans up against a wall. So we can all draw that, I think. The bottom of the ladder is 1.5 meters from the wall. So I'm going to go ahead and underline that. At time t equals 0, and that's important too, basically before we start the clock, and slides away from the wall at a rate of 0.8 meters per second. Well, that's a rate, right? And that's the bottom of the ladder. Okay, the bottom of the ladder is sliding away at a rate of 0.8 meters per second. All right, so when we draw the picture, you're going to see what that looks like. Basically, the ladder is sliding, the bottom of it is moving like this at a rate of 0.8 meters per second. Find the velocity of the top of the ladder at time t equals 1. So last thing I'm going to line is we're trying to figure out the velocity of the top of the ladder at t equals 1. So without further ado, let's go ahead and look at the picture that I drew, talk about what it means. Okay, so just like in the last example where we drew a fish tank, this one we're going to draw a picture, an illustration of a ladder. Okay, now first of all, we don't know the angle, so I'm just going to sketch. Here's our wall and here's the floor or the ground. When the ladder is first leaning, okay, at time t equals 0, it told us that it was 1.5 meters from the wall. So here's the bottom of the ladder. It's 1.5 meters from the wall, okay? And the ladder is 5 meters long. Regardless of how it slides, it's going to remain 5 meters. We'll talk about that in a second. But here's the initial position of the ladder. Now after 1 second, the ladder's still 5 meters, right? But at time t equals 1, it's slid away from the wall, okay? We don't know how far, but we know that it's sliding at a rate of 0.8 meters per second because if you read this, it says slides away from the wall at a rate of 0.8 meters per second. We want to find the velocity of the top of the ladder at time t equals 1. So we want to figure out, I've got a question mark here, basically how fast this ladder is sliding down the wall at time t equals 1. So maybe it's sliding down at a rate of 2 meters per second or 1.3 meters per second going down. What is that velocity? And furthermore, do we have enough information? Well, we should. And sometimes you do get into a problem and you're like, well, maybe I don't, okay? But this one, we are going to have enough information. I'll give you a couple hints here as to why we know that. If we know its initial position and we know its speed moving this way, and we can figure out how long this is, and since we can figure out the length of this, so we can actually also figure out the height. And looking at a related rates problem, from there we can figure out how far down it's going. Okay, So anyways, we'll get to the future steps that will confirm that we have enough information. But for now, hopefully this picture will help you understand, okay, here's the top of the ladder. How fast is it falling at time t equals 1 as the ladder is sliding away from the wall and the top of the ladder is going down? How fast is this? Okay. So that's it for example 2 and the picture for it. Let's go ahead and look at example 3. Okay. It says water pours into a conical tank, so kind of like example 1, except the tank is a cone. So I'm going to underline that. A conical tank, the tank has a height of 10 meters and a radius of 4 meters. And the water is pouring in at a rate of 6 cubic meters per minute. So, with our rectangular tank, it was pouring in at a rate of 3.3 cubic meters per minute. This one's pouring in much faster at a different shaped tank. Here's the question. At what rate, so again, we know this is a related rates problem because we have water pouring in for one rate, and then the question we're asking is at what rate is the water level rising when the water level is 5 meters high? Okay? So it's like example 1 in that we're trying to figure out the rate at which the water level is rising, but it's a cone now. That means the picture is going to be different. So here's our picture. Water is coming in at a rate of 6 cubic meters per minute. Remember, cubic meters is volume. Here is our cone. It says it was 10 meters high and 4 meters as a radius. That's actually pretty big when you think about it. And let's go back and read a few more things here. It says, at what rate is the water level rising when the water level is 5 meters high? So basically, as this water is going to fill up as it goes into the cone. At 5 meters high, at what rate is this water level rising? Now, I want you to think about this problem conceptually for a second. And again, this is why we draw pictures. When the water first pours in, the rate at which this level is rising is going to be much faster than up here because the radius is smaller down here, right? The top radius is 4, but down here at the bottom, it's going to be just, a few centimeters, right? At the very tip. So naturally, the water is going to fill up quicker, or the height of the water, as it goes at the bottom. But as it goes up, the rate at which the water level is rising is going to decrease because you have a bigger radius or a bigger diameter. When you get to the top, it'll be the slowest rate of increase, right? So that's just an interesting thing to think about. If it were rectangular, it'd have a constant rate, right? Because the width or the length of that tank is constant. This one's changing. Now, again, we know this is a related rates problem because we have water coming in, and the rate at which this height increases is going to be based on that, right? It's going to be based on how fast this water is coming in. If the water were coming in quicker, then the rate at which the water level is rising, or the height of that water level, would go quicker. And if it was slower, it would go slower. So we're interested in how fast the water level is rising when the height is 5 meters. And I went ahead and labeled the height of the total cone and the radius. Now remember, the height of the water level is not the same as the height of the cone. The height of the water level changes, the height of the cone does not. Same for the radius of the water level. The radius of the water level is going to increase as it fills up. The radius of the cone will stay constant. So keep that in mind as we go on to future steps for this problem. Okay, let's look at another example. And I think this is our last one. And again, we're just going to look at picture drawing for this particular video, rather. We'll look at one step at a time for these, just because I think it's the best way to teach related rates. And when we get to the next lesson, optimization, I also think it's going to help you as well. Especially, when you're doing a worksheet. I found that my students really excel with these types of problems when they do one step at a time. Okay, it just eliminates the overwhelming sense. I remember when I took this class, I was really overwhelmed with all the steps. When I started doing it one step at a time for each problem, like for example, right now we're just drawing pictures, it really helped me grasp the concept. That's not true for all lessons. I know some lessons it's better just to go ahead and do the whole problem, but for now we're just going to draw pictures today. Okay, example 4. Coffee is draining from a conical filter into a cylindrical coffee pot. So we basically have two shapes going on. Both the pot and the filter are 6 inches wide and 6 inches tall. How fast, now notice I've kind of already got everything circled on here. How fast is the level of the coffee in the pot rising when the coffee in the filter is 5 inches deep and falling at a rate of 1 inch per minute? Okay, so we basically saved the best for last, right? Because we have a little bit more complication going on. Let's go ahead and take a look at the picture that I drew. Okay, most of you have probably seen a coffee filter. Some of them are conical and some of them are more cylindrical, I guess you could say. Anyway, here is a conical coffee filter, and the way it works is you pour the coffee beans in, or grounded coffee beans rather, and then it drips down, and basically the water soaks into the coffee grinds, and then it drips down into your coffee pot, so you can get all buzzed in the morning time and wake up. So it said that if you read the problem, it says that they both have they're both 6 inches wide. So the width of this conical filter is 6 inches, and so is the width of the coffee pot, which is a cylinder. Okay. And it says they're both 6 inches tall, so we can go ahead and label them both 6 inches tall. Now I will tell you this, actually. This is irrelevant. Okay, it's irrelevant how tall, excuse me, how tall the cylinder is. And that's because the rate at which this coffee is rising in this pot will stay the same as it goes up, because the width of this is the same. It won't be, now up here it's different, right? Because as it drains, it's going to drain quicker as it goes down, because the width is going to decrease in a cone. So anyway, sometimes you are given irrelevant information. In this case, it doesn't matter how tall the coffee pot is. Okay. So let's read a couple more things here. How fast is the coffee in the pot rising? So we are ultimately interested in the rate at which this is going up. Okay. Now, actually, it will change. No, I kind of misspoke earlier. The rate at which this is going up will change just because it's coming from this conical filter. Okay. How fast is the level in the coffee pot rising when the coffee in the filter is 5 inches deep? So let's go ahead and label that. Let's say right here, the height of this coffee in this filter is 5 inches deep. Okay. And falling at a rate of 1 inch per minute. Okay. So basically what's happening here is that when it's 5 inches tall, it's falling at a rate of 1 inch per minute. So that's an instantaneous rate, just like the speed of a car, only it's much smaller, right? 1 inch per minute isn't very much, but you can kind of see what that means in terms of this problem. Its speed right here is 1 inch per minute. So for every minute, the height of this falls by an inch. At this particular moment, remember this is instantaneous. So when the height in here is 5 inches and it's going down at a rate of 1 inch per minute, how fast is the coffee in the pot rising? We'll just put a question mark here. Okay, how fast is that going up? Now, we're not asking how tall it is, we're asking the rate at which it's increasing. So that's it for our picture. You can, again, you draw a picture to get a understanding of what you're trying to solve, and it just gives you a better conceptual understanding as well before you start to write out the formulas and use calculus to take the derivative and stuff. So that's it for step 1. We're going to do 4 examples, and just for this video, I'm just focusing on drawing pictures, because I think, in my opinion, it's the best way to learn related rates, doing it one step at a time. If you have any other any other questions about this step of drawing a labeled picture, let me know.